Hello, how are you? In this video we will see should Ampere, Faraday and Lorentz Force laws all be unified through special relativity. This video is brought to you by the Question Response channel, the channel where you will find the answer to everything. Thanks to Brent Meeker, Viktor T, Toth, John Ruth and Hugo LaRue Guthrie for answering this question. We'll start with Brent Meeker's first answer.
They were already unified by Maxwell. Special relativity just showed Maxwell's equations were not tied to some medium in the vacuum.
We continue with Viktor T. Toth's answer.
Maxwell's equations and its kin have a remarkably compact expression in the language of tensors in a Riemann spacetime. There is also a remarkably compact expression of Maxwell's equations in the language of differential forms. One of the interesting things about the Lorentz force is that the relevant Lagrangian is not expressed in terms of the magnetic flux density B, but rather in the magnetic vector potential A. This fact was tested by the Aharanov-Bohm experiment and found to be correct. Which, frankly, is pretty weird. So, they are unified, alright.
What do you think? We will continue with John Ruth's answer.
No need, really. These laws were reconciled already by way of Maxwell's equations. What special relativity accomplishes is to ensure that Maxwell's equations work the same way for all inertial observers, not only for privileged observers who are at rest with respect to some absolute reference frame. If you find my posts useful, please consider supporting my efforts.
The following answer is from Hugo LaRue Guthrie.
They already are, kind of. Maxwell collected the four most fundamental laws of electromagnetism, which are today known as Maxwell's equations. These are Gauss's electric field law, Gauss's magnetic field law, Ampere's law, and Faraday's law. For all of these equations, you will find that they are invariant under the Lorentz transformations of special relativity. A mathematical proof of this can be found in any college-level modern physics textbook, although I recommend looking at the Feynman Lectures on Physics Volume 3. But it doesn't end there. You can also prove that the equations of electrodynamics lead to equations describing magnetism, such as the Lorentz force equation, when applying on them the transformations from special relativity. I recently wrote a paper about this mathematical development. In short, you consider a linear distribution of discrete electric charges that are all in uniform motion. You examine the problem from two different frames of reference. First, you move along with the charges, meaning they are static with respect to you as the observer. In this case you only measure the electrostatic field they generate. In the second case, you are stationary and the charges move relative to you. If they move at relativistic speeds, then Lorentz contraction from special relativity will reduce the spacing between each pair of discrete charges. As a result, the observed charge density in the conductor increases and the aggregate electrostatic field measured is stronger than in the first scenario. This extra electric field is what we call the magnetic field. Through relatively simple calculations I found this extra force to be equal to the Lorentz force. Hence, we can affirm that the magnetic field is a relativistic transformation of the electric field. So to answer your question, the laws of electrodynamics, electrostatics and the laws of magnetism are all deeply correlated by special relativity.
This is the end of the video. Thank you for staying until the end. If this answer helps you, please help us too by leaving a like and subscribing to this channel. It allows us to move forward on YouTube. We are coming to the end of this video. You can continue the debate on this question in the comments with the community. See you soon.